Hello and a very warm welcome to today's presentation. My name is Tim Holm. I am Director of Commercial Strategy and Business Development here at Optibrium and the moderator to today's webinar, Deploying Cerella for Active Learning using Deep Learning Imputation. Today's event marks the official launch of Cerella, our groundbreaking artificial intelligence software platform. So now it is time for me to hand over to our host, Matt Siegel, CEO here at Optibrium, and today's presenters, Greg Shields, one of our software developers here at Optibrium, and Gareth Conduit, the CTO at Intellegens. Matt, I will now hand over things to you.
Thank you very much, Tim. It's a pleasure to be here today. Thank you all very much for joining us online. It's great to see so many familiar faces and also lots of new people joining us. So you're all very, very welcome. This is a very exciting time for us. We're going to be talking about the culmination of over 3 years of research and development. We're announcing our new product, Cerella, which brings the Alchemite method for deep learning imputation for active learning and drug discovery, and it provides a scalable and secure platform to interactively apply this proven method to your projects and to your data. I'm very pleased to be joined today by Gareth Conduit. Gareth is a Royal Society University Research Fellow at the University of Cambridge. He's got a track record of translating research to industry, exemplified by taking machine learning methods from the supervision of a PhD project all the way through to commercialization through his startup, Intellegens. Gareth is Chief Scientific Officer at Intellegens and will be telling us more about the Alchemite method they've developed. I'm also pleased to be joined by my colleague, Greg Shields. Greg Shields is a principal software engineer here at Optibrium and was one of the leading developers on the Cerella project. He has a natural sciences degree from Cambridge and a PhD in structural chemistry. He's been in software for over 20 years, so brings an enormous amount of experience to our team. So today what we're going to do, I'm going to hand over to Gareth in just a couple of minutes. He's going to tell us about the Alchemite method for deep learning imputation. Then I'll tell you a little bit about some of the applications to which we've been applying Alchemite across a range of different applications in drug discovery. Just give you a very high-level overview of the various diverse and successful applications that we've seen before introducing Cerella and show you how you can actually deploy this method for active learning. Greg is going to give us a demo and actually show us Cerella in action through our Stardrop software before we wrap up, draw a few conclusions, and of course answer any questions that you may have. So first of all, where did we really start this journey? We started this journey by looking at the very trendy area of deep learning and saying, well, how can it actually apply in drug discovery? And what we discovered, along with many others, is that if you just take your sort of favorite off-the-shelf deep learning method and apply it to traditional QSAR modeling, it really doesn't offer much of an advantage. Bob Sheridan from Merck, who I notice is in the audience today, he gave a really great talk a couple of years ago in Switzerland where he described an experiment where Merck applied random forests, their in-house QSAR method at the time, to 30 large, high-quality QSAR data sets, and also made the same data sets available to a number of different research groups exploring deep learning methods. And while they did show an improvement, the reported average improvement of the best method over those 30 data sets was only 0.04 in the R-squared. So that's an improvement, but it doesn't qualitatively change the way in which you can use these models to make decisions in drug discovery. And to get there, you're applying an enormous amount of additional computational effort and complexity to get this really very sort of marginal improvement. Now, since then, there have been other advances in graph convolutional methods and so on, but still, I think the overall conclusion remains the same, that if you just try to build QSAR models using conventional deep learning methods, certainly your mileage may vary. You see some big improvements, but most of the time, on average, there really isn't a huge difference. And we understand the reason for this. It really comes down to the challenges of the data that we deal with in drug discovery. The data that we have is very sparse. If we think about the bioactivity and property data, no compound has been measured in every assay of interest, and no assay has been run on every compound of interest. And typically, if you look at, say, a global pharma data set, less than 1% of the potential compound assay measurements have actually been made. And relating to that is the fact of what we think of as sort of big data in pharma really isn't very big. We might have in a global pharma company the order of sort of a low number of millions of compounds and maybe tens of millions of experimental data points. But on the scale of a sort of a Google or Facebook sized data set, this really isn't very large at all. And even worse, the data that we do have is very noisy. We know that data from a biological assay will typically have between 0.3 and 0.5 log units of experimental variability, even in the same assay run by the same team in the same lab. So the question that we set out to answer is, well, how can we learn from these sparse and noisy experimental data in a different way, in a better way, to make improved predictions for the bioactivities and properties of compounds in which we're interested? And the solution that we settled on is a method called imputation. And so I thought I would, just before handing over to Gareth, really introduce this as a concept. And of course, we're all familiar with predictive models. We all use QSAR models. And essentially, a predictive method takes a set of input features, in our case, molecular descriptors. So we calculate descriptors for our compounds. So here we have a matrix of descriptors for all of the different compounds. That is a complete matrix because we can calculate every single value for every descriptor, for every structure. And we feed that into our favorite modeling method, sort of illustrating a sort of a random forest here, but it could be an SVM or a multi-target deep neural network or whatever it might be. And we build one or more models to make predictions for the properties in which we're interested. So the purple squares here on the right-hand side. Imputation is quite different. With imputation, what we do is we take the limited data that we have available. Here, this sort of sparse assay data. So we've got the assays and the compounds. The green squares represent the measurements that have been made, but as I described, most of these are missing, the white space in this matrix. And we use that limited data that we have available to fill in the gaps, sort of illustrated here by the purple squares on the right-hand side. And so it's this process of imputation that really is key to the Alchemite method. And I'm now going to hand over to Gareth, who's going to tell us more about Alchemite and the work that they're doing at Intellegens. So over to you, Gareth.
Thank you, Matt, and I'm ever so excited to be here today to be able to share with you the Alchemite story. It's very exciting to now see that being brought into the pharmaceutical sector through the release of the Cerella product. Now, the development of Alchemite started in my group at University of Cambridge and a couple of successful PhD student projects before we then took it into a startup that I am a co-founder of called Intellegens. And when we were developing Alchemite, we were aiming to solve precisely the problem that Matt described, the problem of can we apply the powerful methods of machine learning to real-life experimental data. Can we apply the methods to experimental data that is both noisy and also experimental data that is sparse, meaning that not everything has been measured? This is typically a difficult problem to do because there is a lot of missing values, and that is a real handicap for standard off-the-shelf machine learning methodologies. However, we developed Alchemite to overcome those obstacles, and it can do that by merging together all available experimental data about a system, and furthermore merge experimental data together with first principles computer simulations that can learn from all the possible information there is to get the very highest quality predictive method. Once we have that model in place, we can use it to impute the sparse data, we can use it to predict new values for new materials, new drugs that have not previously been made, and ultimately in order to discover brand new materials and drugs. Now, because we're able to have these very high quality models, it can then circumvent the need to do additional, very expensive and very time consuming experiments so we can get to that final answer quicker. Now, the underlying methodology that we have developed, the Alchemite tool, is generic and could be applied to almost any problem, focusing on those with sparse data. But we initially developed it for the field of material sciences, And we're now very excited to also bring it to small molecule drug discovery. And so today I'm going to briefly give an overview of machine learning before going through one case study of the use of Alchemite on a real-life materials design project, for summing up and then handing back to Matthew, who will tell us about all the wonderful applications to pharmaceutical problems. Now, in a nutshell, machine learning is just a black box. We have an example here in which on the left we have the composition of a typical material. It's the same as the atoms that go into a molecule. They will be passed into this black box at the center of the slide. That will do some clever maths, and out on the right will be predicted the properties of the material we are interested in, or the properties of the drug, the activity levels of it. And at the top, we've got the melting point, then the ability for 3D printing in this case, and then down the bottom, for example, the fatigue life of the material. Now, for the central core for that machine learning core, the variety of off-the-shelf methodologies available, and one that is currently very fashionable is a neural network, which is a mathematical representation of how perhaps maybe it is thought the human brain might work. So to do that, we have to provide it with a database of pre-existing materials knowledge. So on the left here, we've got the known compositions, the material, and on the right, the properties. And we feed those in to train that machine learning tool. And you can see that it's now got color. It's been developed to the center here. And then once it is, then we can present the tool with a brand new material that it has never seen before. And then it will make high quality predictions for those properties. And then the ultimate use case is often discovering new materials, so we can get the tool to scan through millions, billions of different possible materials. It will do each one in less than a millisecond until it hits upon the one that would have the right material properties for our client's end use case. And of course, that's a lot quicker than doing millions of experiments, particularly in materials where they cost about $100,000 a go and would take 6 months. Instead, we can do it in a millisecond. So that's the goal of machine learning. But in the application to real life problems, particularly when we're based on experimental data, we're going to have a big handicap, and that is that we don't know everything about each experiment. So we represented this here with some blacked out information that it could be we don't know the entire chemical structure, or over on the right, it may have been that some of the physical properties have and others have not been measured. And this is where the typical machine learning methodology is going to fall flat, but we have developed the Alchemite tool that it really thrives in such a system. So once we have the machine learning tool in place, we can then apply it to real life problem. And I just want to show one case study that we have done working with Rolls-Royce, that they wanted to further the design of their engines. And in particular, they wanted to 3D print some of the components right at the heart of the engine so they could get them into a more intricate shape to improve performance. But the problem is 3D printing is a new process, and it requires new and fine-tuned alloys that will work particularly well. And so we were tasked with, can we train a machine learning tool to find these alloys? We got all the experimental data. It was very sparse, in fact, impossibly sparse in for some properties, but we nevertheless trained a model using Alchemite, and this is the material that we were able to propose. It comprises 10 different elements. We've got all the concentrations of those here, and this is a much more complex alloy. It just contains more elements than the current generation of alloy, which would contain up to 6 or so elements. And this immediately shows us the first advantage of machine learning is that we're able to explore a more complex design space, but because we're not limited by the time and it would take to go through all of those permutations in experiment, and so could find this more complex alloy, just giving us that opportunity. And in the bottom right, we see that we have also proposed or specified the design parameters for the alloy, how quickly it is printed, this exposure parameter, and also a treatment that you apply to the alloy after it has been printed. And so with that in place, the real proof of the pudding is going to be in the eating, and so we could pass this proposed composition and other processing variables across to our colleagues at Rolls-Royce, who then put it in their 3D printer, made it, then look at it under a microscope, and this is what it looks like. It's the two-phase material. It's got two different alloy compositions inside of it, and which you can see from that black speckled pattern, and that is vital to give the alloy its strength. And in a cursory look here, it looks like there are no defects that are formed. There's no obvious cracks in this that have been formed during the printing process. But that is so important that we should go in and measure it more carefully. So here we have a graph of the number of defects formed in printing as a function of one of the parameters. That's basically how quickly do you do the 3D printing, how much power do you put through the laser. So for the alloy to work well, we want very few defects to be formed. So we need to be at the bottom of the graph, actually in the grey shaded region. And we see for the exposure parameter that we recommended, that 0.8, I've highlighted that with the cyan arrow, we can see the experimentally measured number of defects is indeed low. It's about half the maximum possible defects that would be tolerable. And so the alloy has experimentally worked for this property. And in fact, it isn't just this property that we're interested in. There are many other physical properties that we don't have time to share today, like the strength of the alloy, the cost, the density, oxidation resistance, and so on, all of which were experimentally verified, and you can read about them in this peer-reviewed paper down here. And this alloy is now, of course, also being further taken forward to production by Rolls-Royce. So that's just one example of the use of machine learning, but there have been a whole slew of other examples. Today I'll just share three of them that are in the chemical space. There's more interest to the audience. We got at the top the design of new cathode materials for batteries that we've done alongside Samsung. Next down is the design of new lubricants that we have done with BP. And at the bottom is the specification of new kinds of inks that we have done with Domino. And that's just a handful of all of the projects that we have been involved in. And so to summarize, I'm very excited to present today our Alchemite machine learning methodology that has a real power and capability to work on sparse data. And it can do this by merging together all sources of knowledge about a system, be it both experimental and also first principles computer simulations. And we've used it to successfully model many properties of materials, and I've shown today the one case study of the alloy for 3D printing with Rolls-Royce. But we've worked with many other companies, and my startup Intellegens is already successfully licensed our underlying Alchemite 2 tool to a large number of different companies that are already using it in their design process, several of which have led on to design of materials that have already been experimentally verified and are now undergoing real-world testing. So if you want to learn more about that, we've got some links down the bottom. We've got an online demo to design some steels, and also a whole heap of peer-reviewed papers that contain materials we designed and experimentally verified. And we're also very excited to be bringing the same Alchemite methodology from materials across the pharmaceuticals. And now I turn back to Matt Segal to hear more about that. So thank you, Matt.
Wonderful. Thank you very much, Gareth. That was a great introduction to Alchemite and the fantastic work you're doing at Intellegens. What I'm going to do now is really talk about how this method can be translated into the world of drug discovery. And so first of all, let's just think about the sort of modeling that we want to do. So first, Alchemite can take the descriptors that we're all familiar with from our computational chemistry approaches as input as well. So we can still have our matrix of descriptors, the orange squares on the left-hand side, to learn from the structure-activity relationship between those compounds and the various assay measurements that have been made. But as Gareth also described, it can take this sparse and noisy experimental data directly as input as well. And by doing that, it can learn directly from the relationships between those different experimental endpoints, as well as the structure-activity relationship. And what we've shown now in repeated studies, and I'll give you some examples in a moment, is that this makes much better use of that sparse and noisy experimental data that we have than conventional QSAR models. So it can fill in the gaps, as we described, the purple squares here on the right-hand side, but also you can tell the model that for some compounds, it won't get any experimental data. So maybe we only have the descriptors because it has not yet been made and tested. And so it can also make predictions for virtual compounds. And what we've shown is that it makes more accurate predictions. And of course, that's what we're after, to target the high quality compounds for our project. The other very important feature of Alchemite is that it doesn't bring just a single prediction for each value for each compound. It actually generates a probability distribution over possible values, sort of illustrated here by the purple histograms at the bottom. What this means is that it can estimate the uncertainty in each individual prediction. So sometimes you see a distribution like the one on the right-hand side here, sort of very broad, very smeared out. That's the model saying, look, I'm not really sure. The value is somewhere around here, but it's got a very big error bar. Whereas in other cases, you see these very sharply peaked probability distributions, like the one here on the left-hand side. That's the model saying, yes, I'm really confident in that value. It's got a small error bar. And of course, these are the ones we're most interested in. We're most interested in the most accurate or the most confident predictions, because as we'll show, they're also the most accurate, and that enables us to use the best data to make the decisions and target our high quality compounds. Incidentally, of course, it also helps us to prioritize experimental resources, because of course, where we have the greatest uncertainty, like on the right-hand side, is where that experimental effort is going to add the most value. So having sort of summarized the method, the question is, well, how does it work? And so the first thing that we did, working with our colleagues at Intellegens, was to do an initial proof of concept study. So this was published about 1.5 years ago in Journal of Chemical Information and Modeling, and we also presented a webinar back in early 2019. This was a simple proof of concept study applying Alchemite to a data set of sparse kinase activity data. This was actually published by Eric Martin and his colleagues at Novartis, actually as a test for their PQSAR method. So this data set had about 13,000 compounds and 159 experimental assays, but only 5% of those possible values had actually been measured. 95% were missing. And they also constructed this with what they described as a realistic test set. So this represented the extrapolation in chemical space that we see in a chemistry project. We train a model on what we know about, but then in the course of a project, we move outwards to new chemistry and new chemical space. I'm not going to go into enormous detail here. You can see the details in our webinar and the presentation and the publication. But what you can see here is looking at 100% of the independent realistic test set, Alchemite came out to have the best result overall in terms of the accuracy. So here we're showing the root mean square error. So a lower value is a smaller error on average and represents increasing accuracy. And we've compared this with a number of other machine learning and deep learning methods as well. And an imputation method, the PQSAR method, also does very similarly to Alchemite on that test set. But actually, another very exciting result here is when we move left down this x-axis, what we are doing here is focusing on the most confidently predicted results from that independent test set. So where the model thinks it has the greatest confidence, and what you can see is as you move from right to left, the accuracy also increases. So there's a very strong correlation between the model's confidence and the accuracy when you actually compare that with the observed values. And that's exactly the behavior we're looking for. So proof of concept is great, it works very, very well, but it's not representative of a real application in drug discovery. This is all kinase data, it's very homogeneous, and so on. So the next thing we wanted to do is say, well, how does it work in practice? And we were very pleased to collaborate with our friends at Constellation Pharmaceuticals, and we worked with them on application to project-specific data. So this was data from 2 different projects, and most importantly, it was very heterogeneous. So not just biochemical activities against the target, but also phenotypic screens and a range of ADME properties. This was also a relatively small data set, about 2,500 compounds by the end of this project across these 18 endpoints. And this is also interesting because most deep learning methods need very big data sets to get an advantage over other machine learning methods. We wanted to see, would it apply at this limit of quite a small number of data points and compounds? And I guess in a nutshell, the answer is yes. You can see here where we compared it with 4 different QSAR methods for each of the endpoints, and in each case actually picked the best result for the QSAR method on the test set. You can see that Alchemite, trained across this entire data set, a single model, achieves a substantial improvement in the average R-squared, showing a really great improvement in accuracy. If you want to know more details, please see our paper that was published just earlier this summer in Journal of Chemical Information and Modeling that goes into details about the different data sets, the different applications, prospective prediction, and so on. We were also presented a webinar in April where we were very pleased to be joined by Julian Novell, the Vice President of Drug Discovery at Constellation. He spoke about how they actually used these results in practice and the value that they saw. And just as one example, he noted that there were very few false negatives amongst those confidently predicted inactives. Again, using this benefit of being able to put confidence on each prediction. So where they saw a confidently predicted inactive, they could have actually avoided making that compound and making a very substantial saving in unnecessary synthesis and in time. At the other end of the scale was a collaboration with Takeda. Takeda in Boston. This is applying Alchemite to a global scale pharmaceutical data set. So over 700,000 compounds and 3,500 experimental endpoints. This is one of those examples where the data set was actually less than 1% complete in practice, and it covered, again, a broad range of drug discovery assays, compound activities, phenotypic assays as well, ADME properties, and so on, high throughput screening. We presented a webinar again back in May. You can find a link on our website there, where we discussed all different applications to prospective prediction of target activity, to prediction of high throughput screening data, to a broad range of ADME properties, and so on. And we were very pleased to be joined by Scott Rowland from Takeda, who spoke about how they actually use those results. And one thing he said that really struck home was, the way he thinks of it is that this is an extension of what a medicinal chemist does naturally in the course of a project, looking at the relationships between the different compounds, the different data, the different endpoints, but on a much, much larger scale than any person or even a project team could do. And on the right-hand side, you can see a substantial improvement again from Alchemite over, again, a conventional QSAR modeling method. We looked at random forest. Here are the endpoints ordered from the most accurately predicted on the left to the least accurately predicted on the right. The R-squared, the coefficient of determination on the y-axis. And this shows a sort of profile of accuracies across those different endpoints. Alchemite achieved a really substantial improvement in the median. So 50% of those endpoints had an R-squared above 0.5. Whereas the median R-squared for random forest was only 0.19. Looking at another collaboration, this time with open source malaria, we looked at how the models built with Alchemite could be applied in combination with generative methods to suggest new compounds for synthesis and testing. This was actually a competition run by the open source malaria project where they looked at application. They made a data set of sparse antimalarial data available, made that available for anyone who wanted to try and build a model, ran a blind test, so making predictions on a blind test set, and they ranked the models and chose the top 4 of those models, including Alchemite, to go forward for the next stage. And the next stage was to then apply those models in combination with generative methods. In our case, we used the NOVA module in our StarDrop software. The compounds that were generated, the ideas were prioritized with the Alchemite models. And here we looked for a good activity profile across antimalarial endpoints as well as good physicochemical properties. And what we did here was we didn't propose the compound that was predicted to be most active. Again, we used this advantage of Alchemite to propose the compound that was most confidently predicted to be active. This then went forward. The OSM team synthesized and tested that molecule in vitro, and of the compounds submitted to that project, the only one that was found to be active in practice was the one submitted by ourselves and our colleagues at Intellegens. This recently was summarized in a paper, and also we had a webinar on the 9th of June where we were very pleased to be joined by Professor Matt Todd, who leads the open source malaria project. And one of the things he pointed out is the specific change that was proposed and predicted by Alchemite to be active was not something that the chemists involved in the project would ever have conceived of. They thought they had explored, in this case it was modification here in the sort of top right region of this compound, they thought they had explored all of the sort of SAR around that and couldn't find any avenues forward. And this actually gave them a new direction for optimization in the context of their project. And one last example is a collaboration with AstraZeneca looking at prediction of in vivo properties, in this case, in vivo rat pharmacokinetics. The inputs here were sparse in vitro ADME data as well as in silico ADME predictions and compound descriptors. This was tested on an independent chronological test set split. And we looked both at the prediction of pharmacokinetic parameters, but also direct prediction of the concentration time curves, the PK curves, summarized here. And this is basically the most accurately predicted curve in the test set to the least accurately on the right-hand side. And just to show you what this looks like here, the best prediction has a very high correlation. And you can see here the blue line represents the experimental concentration time curve. The purple is the predicted. Of course, that's the best prediction. So let's look at a most representative. This is the median value here. And again, you can still see a very strong agreement between the experimental and the predicted curves. So here, of course, the advantage is by making predictions of the in vivo disposition, the in vivo pharmacokinetics based on in vitro ADME data, one can make better decisions about prioritizing compounds for those very expensive and time-consuming experiments. So that was a very quick run through a number of different applications. I hope you'll be able to look up the webinars and listen in more detail or read the papers about that, or indeed attend our webinar on the 11th of October about the project with AstraZeneca. But hopefully that's just given you a demonstration of some of the benefits provided by Alchemite and our augmented chemistry platform to extract additional value from your compound data, highlight those relationships between the structures, activities, and other properties on a scale that can't be achieved by a medchem team using conventional tools, as pointed out by Scott Rowland, and better support chemical space exploration beyond conventional QSAR models. Again, the open source malaria project illustrated that. The goal, of course, is to accelerate your discovery cycles, so reduce the number of compounds needed to be synthesized. We saw an example of that in the Constellation project, and focus on the most valuable experimental measurements to make. And also by using the confidence in the values, it increases our ability to make good decisions in terms of lead selection and progression of compounds by using these accurate uncertainty estimates for prioritized compounds, essentially with the highest chance of success, but also, on the other hand, avoiding missed opportunities. What we don't want to do is reject compounds where there's a lot of uncertainty. We don't want to miss that opportunity to progress a potentially good compound. So, with all of that preamble about the methods, some examples of how it's been applied, what we're really here to do is to tell you more about our Cerella platform. And so Cerella, for the first time, will enable deployment of Alchemite for active learning in the context of your drug discovery projects. So what does Cerella do? First of all, it connects with your data sources. So it can automatically update and bring in the latest experimental data. It will prepare that data for modeling. So it will apply appropriate transformations into units for modeling. It will apply any sort of cleaning or business rules and populate that sparse matrix that we've been talking about, the green squares here on the right-hand side. It will then automatically build and, of course, update models as new data become available. It builds both imputation and virtual models. So with the imputation model, of course, you can fill in the blanks for the compounds that have already been synthesized and tested in some experimental assays. And with the virtual models, make predictions for as yet unmade, untested compounds. Now, if our initial experimental data is only 1% complete and we fill in all of these blanks, suddenly you have almost 100 times more data to deal with. And we may be talking of tens of billions of data points. And so we've also engineered Cerella to deal with what we describe as the massive matrix problem, to make that data very easily accessible, very easily searchable, to find the most valuable information, the most valuable compounds for your project. And all of this data, all of these models are made available through our Stardrop software, as we'll demonstrate shortly. But of course, we recognize there are many ways you might like to look at these results, process these results, different front ends you might want to use. And so it's a very open platform. We have implemented a RESTful API so that it can link with any other platforms that you wish. It's a very open platform. So how can we apply this in practice? Well, here are a few examples of the questions that we can answer with Cerella. We describe this process of sort of filling in the missing data and proactively highlighting high-quality compounds. We want to identify our new opportunities with confidence. But what we don't want to do is just dump some massive matrix of data for you to sort of visualize and search and sort through. We want to answer this question in a much more natural way. So you can think, typical workflow might be to perform a query of your experimental database. So here's an example where we're looking for a compound with good target activity, good permeability in CACO2 cells, good solubility. And of course, we can execute this query. This is Stardrop's query interface. You can go to the database, find the compounds that have been measured to meet those criteria. But simply by ticking this extra box, it will also go to that massive matrix and say, hey, are there any other compounds that with confidence are likely to meet those criteria? And it will bring them back as well. So here you can see the white squares here represent the values that have actually been measured experimentally. But you can see these blue squares are those that have been filled in with the imputed values that have sufficient confidence to say, hey, you might like to take these forward, test that to validate that hypothesis. These could be very valuable compounds for your objectives. Another question we could ask is, well, how do the actual experimental results compare with the imputed values? Remember, for each of the imputed values, we have a probability distribution, the sort of bell curves that I was showing you on an earlier slide. And if, for example, that measured value lies way out on the tail of that distribution, that would be a very unlikely result based on all of the other evidence in your experimental data. This could be an experimental error, an artifact or an impurity in your experiment. It could be misleading data. Or on the positive side, it could be really unexpected structure-activity relationships, something that will be really valuable to understand to guide further optimization. So you can see here the little sort of purple squares represent something that's identified as an outlier. We can click on that and drill down. And here you can see the probability distribution sort of shown by the blue histogram. And here is the measured value in red. In this case, this measured value is way off on the sort of negative tail of that distribution. This is a potential false negative. Alchemite in Cerella thinks that this is very likely to be an active compound, but you can see it's been measured to be inactive. We might want to go and retest that because it could be a very valuable starting point for our project or interesting SAR to explore. Another question we can ask is, well, if we want to make the best decision to progress compounds perhaps to a downstream and expensive assay, what are the most valuable experimental measurements we can make now, maybe in cheaper, higher throughput assays, to make that decision with greater confidence, to predict the best compounds for that downstream assay? And so what you can do here is you can pick an assay, in this case, maybe a cell-based assay. You can say, that's my target. That's what I want to make better predictions for. But here are some additional measurements that I could make, maybe with my earlier higher throughput assays. And what you can say is, well, what are those most valuable experiments to run? So here you can see it's suggesting to measure the activity against a target and permeability. These are the assays with the most measurements. You can even click on this and say, well, what are the specific compounds that will add the most information in that assay to make better predictions downstream to select the best compounds? Sort of design of experiments, but in a very sort of user-friendly, very easy way. And lastly, of course, these are all endpoints are all available as virtual models. So just like any other model, you can select them. Again, I'm showing them here within Stardrop. You can take your virtual library, you can run all of the endpoints that are relevant to you. And I guess in our world, we would suggest very much taking a multi-parameter optimization strategy to find those compounds predicted to have the best balance of properties for your particular objective with the highest confidence, so you can make those decisions of which compounds to synthesize and test. Now, I've shown some screenshots here in Stardrop just to emphasize again that this same endpoints, these same measurements, these same models are available through any platform that you want and the RESTful API. But at this stage, I'm actually going to hand over to my colleague Greg, and he's going to show you live within Stardrop how you can actually interact with these results and these models. So over to you, Greg.
Thank you, Matt, for your introduction. As Matt says, I'm going to be showing how we can access the results of the Alchemite models through the Cerella platform in the Stardrop interface. In order to do that, we first need to provide login credentials to the Cerella platform. So this means that any corporate data you may have in your data sources is password protected. I'm going to open an existing project data set, demo purposes. So the first thing I'm going to demonstrate is how we can search both the measured data in a corporate database with the imputed values, which are stored in the massive matrix in the Cerella platform. So these are values where we've run Alchemite models and we've cached the results to enable them to be searched and retrieved easily and effectively. So I'm going to bring up the query interface. This is an existing add-on to Stardrop. And I'm going to search for compounds which have a log P of between 1 and 2, and the value of a PIC50 greater than or equal to 7. This demo is going to be using a public domain data set with activity data for a range of targets. I think Matt has demonstrated a number of studies on corporate data of a much more diverse nature, but we're not able to share those within the platform. What we are able to give this demo with some public domain data. So the important thing, as Matt already pointed out, is if we tick this box, search Cerella values, then we're going to be retrieving compounds which have both measured activity values greater than or equal to 7, but also compounds whose PIC50 values for that particular assay are predicted to be greater than 7 by the Alchemite model. So I'll just run that query. Wait a few seconds. Then a new data set will be created in Stardrop with the results from that query. And as Matt mentioned in his slides, the blue values represent imputed values or predicted values from the Cerella platform, and the white background are the experimental values. So you can see in this case that this is actually a very sparse data set. The majority of the values have been filled in by the Alchemite model. If I just turn on the display of uncertainties, we can see that each of the predicted values from Alchemite has an associated uncertainty measurement. This is derived from the probability distribution, which Matt showed earlier. I'll turn the uncertainties off again to make it clearer. I'm also going to show now, these are some examples of some compounds from that public domain data set. These are in fact taken from Kemble. And another workflow is if you already got a data set with compounds in it, we can run the Cerella models to fill in the values of the assays of interest. In this case, I'm going to choose some of these activity values. I'm going to choose a selection of 8 of these models. And if I click the Go button, then again, I'm retrieving from the massive matrix store both measured and imputed values for these compounds, because these compounds are all in the data set that was used to train the Cerella model. Both the experimental data and the property data are all included to get the best possible value, imputed value we can for these compounds. And again, you'll see that where experimental data is available, that will be retrieved when running the models, as well as when we query the data sources. And again, you can see that the majority of values for this data set come from the Alchemite models. If I scroll down a bit further, you'll notice that this cell is highlighted in purple. This means that this is an outlier and that the experimental value differs from the value predicted by Alchemite by more than 2 standard deviations. If I right-click on that cell, I can show the probability distribution. And in this case, you can see that the measured value, which is highlighted here in blue, is greater than the value of the majority of that distribution. The quality of these distributions does vary depending on the particular endpoint we're studying. But you can see here that in this case, Alchemite is predicting that this value of 7.4 is likely to be an outlier. So this might be unexpected structure-activity relationship, which isn't captured by the current descriptors or by the other experimental data in this model. If I want to improve this model, one of the ways we can do that is to use the suggested measurements functionality. As noted before, this is quite sparse data, but we can use Alchemite to guide us to which measurements would most improve the predictions for the target endpoints of interest. So if I am interested in improving the predictions for these 3 assays, I can go to the Cerella suggested measurements function. And for the purpose of this demo, if we believe that the 5 assays I've selected here are cheaper and easier to measure than the ones I'm interested in improving the results for, I can use Alchemite to predict which measurements are going to make most impact to improving the predictions of the 3 assays I've highlighted here. If I just wait a few seconds, Cerella will return the suggested measurements. So in this case, I'll just make this a little larger so it's clearer. So this is suggesting, in this case, the top 50 measurements come from these 2 assays, and in fact, 40 of them come from this one. So if we only wanted to run one assay to improve the model for the target endpoints of interest, we would choose to measure this one, and then we wouldn't waste resources on measuring the assays which wouldn't really make any impact on the measurements we want to improve the predictions for. I can, if I want to, create a data set with these suggestions in, and then all the usual features of StarDrop are available to export and analyze those suggested measurements. As Matt mentioned, we can also make predictions for virtual models. So here I've got a selection of drugs and drug-like molecules which haven't been used to train any of the Alchemite models, but we can still make virtual predictions. So if I run those same models again, we will see predicted values for most of the cells. Now, there are a few which are blank there, and these are cases where the uncertainty in the Cerella value is so great that the model cannot resolve the Cerella value within the range of measured values. So in simple terms, that value is not likely to be meaningful. So in those cases, we hide the predictions from Alchemite, so you can focus down on the values which are likely to be meaningful for your endpoints of interest. Well, that hopefully gives you a quick overview of how the Alchemite functionality of the Cerella platform can be accessed in Stardrop. So I'll hand back to Matt, who will just make some concluding remarks.
Thank you very much, Craig. That was a great demo, and hopefully you could see how easily you can access these very important sets of data, the very important results, and answer some of these key questions in a very sort of natural way. In this case, of course, we've demonstrated this in Stardrop, which is our software, because that's where we've developed our front end. But as I mentioned, you can actually use any application to access the results from Cerella, and present those however you wish to your users, or analyze them however you would like. So I guess the final question we want to answer here really is, well, okay, that's great, but how can I deploy Cerella? How is Cerella actually put these results in our hand? And I guess the two key points we really focused on in the development of Cerella was the combination of both security, because of course your data is very important and the confidentiality of that data is key, but scalability, to be able to build these models and then search this massive matrix of data for the largest of the global pharma companies. So what we've developed here is really a very unique sort of hybrid on-premises and cloud architecture. So you can see there are two zones here. The blue zone on the right-hand side, this sits within your private network. So here's where your company databases lie, the client applications, Stardrop, or whatever else you use to analyze results and present them to the chemists and other project team members. And on the left-hand side, the green zone sits within a virtual private cloud. This is a single tenant virtual private cloud, so there's no chance of mixing up with other companies. Each company has its own private cloud installation. But within the blue zone, the query service here gathers the data from your database. It then passes it to the Cerella service, and the Cerella service strips out all of that most sensitive information. So the compound structures are removed, the descriptors are calculated, the structures are removed, any assay identifying information is removed, unique and anonymized compound and assay IDs are generated. So all of that data is anonymized. It is then encrypted, and only that encrypted and anonymized data is passed to the green zone here in the cloud. That provides us the scalability and the resources needed for modeling the very largest of data sets, and handling and searching that data here in the green zone. When the results are returned back to the Cerella service here, they are de-anonymized, decrypted, and joined up back with the structures and the assay information to pass to the client applications. So it gives us that blend of security and scalability. And of course, security is absolutely key. So Cerella provides a multi-layer security infrastructure as well. So this is the image I just showed you before. But as I mentioned, the green zone resides within a virtual private cloud. This could be hosted by you or hosted by us. Either way, we're very happy to provide that service. We typically work with Amazon Web Services, but again, this could be installed on another cloud. But by doing that, we can really take advantage of the security model provided by AWS and their virtual private cloud architecture. The modeling system itself is implemented in Kubernetes with a very strict ingress and egress policy and access policy as well. So there's another layer of security there. A third layer of security is provided by our authentication, authorization, and accounting service. So this makes sure that only authorized users can access data to which they have permission. And you can divide that up user by user so that you can really restrict access only to the appropriate data for that user. And of course, the most sensitive information all sits within your private network, that blue zone that I showed you before, which is of course protected by your firewall and your security infrastructure. And all of the communications between these components are encrypted. So we use an encrypted mesh network to make sure that even if anything were intercepted, there's no way that that data could be revealed as well. So in conclusion, I hope we've demonstrated to you how the Alchemite deep learning imputation method can gain much more value than simple predictive models from experimental data, helping to confidently identify high-quality compounds, prioritize experimental resources, accelerate discovery cycles, but also, importantly, avoid missed opportunities. I've given you a few snapshots to show how we have successfully applied Alchemite in a whole range of scenarios, from large sort of global chemical space, global pharma data sets to small project-specific data sets, very heterogeneous data covering a whole range of different drug discovery endpoints. We've shown the combination with generative methods and even the prediction of in vivo disposition. And then we've shown you our new Cerella platform. This enables you to interactively apply Alchemite to your projects and data in this scalable and secure environment. So I hope that's been interesting to you. If you'd like more information on how you can access Cerella, please do contact us. The email address is very simple. It's just info@optibrium.com. And with that, what we will do, first of all, is to acknowledge, most importantly, the team who actually did the hard work. Gareth and I get to stand up here and take the glory. But of course, this is several years of hard work by a lot of people. So here at Optibrium, Greg, who you've met, but also Alex, Graham, Stefan, and Ed. At Intellegens, Tom Whitehead, their head of machine learning, and also Robert and Ben. And I should also mention that the development of Cerella was partly funded by Innovate UK, and that was a project in collaboration with Medicines Discovery Catapult as well. And now, we're very happy to answer any questions you have. I can see a number of questions have already come in, so that's fantastic. We'll get through as many of those as we can. I realize the hour is up, but if you wish to stay online, please do so, and we'll be happy to answer as many questions in a reasonable proportion of time. So I don't know if you want to join me, Gareth. I'm sure some of these are for you, and I'll see what we've got. So there was one question, which is relating to, actually, there's a couple of questions relating to the pharmacokinetics prediction. I will emphasize that we're going to be speaking about those in much more detail on the 11th of November, but I'll try to answer your questions now. Says, since we optimize for humans, any thoughts about how to translate animal curves to a human curve? I think that's a really excellent question. So here we were working with rat PK data. Obviously, there's a nice, large and rich data set that we were able to work with to build and validate that model based on rat PK. But of course, ultimately, we want to look at human PK. So yes, I mean, absolutely. One of the things one could do is to take that sort of early drug discovery data, sort of preclinical data, rat PK, maybe even human in vitro experiments against human cell lines, human microsomes, and so on. And actually look at that translational question of how we can then predict not only PK in humans, potentially actually clinical outcomes as well. And indeed, I believe that our colleagues at Intellegens have already done some work on sort of prediction of clinical data with Alchemite.
Yes, Matt, you're absolutely right. Thanks for pointing this out, that we've had a very exciting collaboration with A-STAR, a research institute at Singapore, where we have applied Alchemite to predict therapies involving stem cells for helping relieve arthritis. There's just been a peer-reviewed paper out about that we're very excited about, and we're now pursuing some follow-up projects.
So also related to the PK question was a question about why in some cases the prediction of the PK curves were not as good as we would have liked. They're bad in these words. And of course, you know, sometimes you get predictions that aren't very good. And that is the case. We are again going to speak about that in more detail, but a key point there is that often those were the cases where there was greatest variability between the different animal experiments itself. So there were multiple replicates done, and sometimes you can see a great deal of variability between the different animals in the study, and those were often the ones that had the lowest accuracy of prediction. Whether that's because there was a large variety in the actual PK for that compound, individual variability, or whether there was an artifact in the experiment is hard for us to tell without going back to the original data. But that was often the case that we observed. Another question is, who is going to use this new tool? Expert users, medchem experts, associates, and so on. And I hope you've seen how easy it is to use. You don't need to be a data scientist or a computational expert. We've obviously illustrated how this can be presented through our Stardrop software, and hopefully you can see how you can ask these questions and gain these valuable answers in a very natural, sort of intuitive way. So we very much believe this should be tools that are accessible to all the decision makers in the context of a drug discovery project. There was another question, says, will this be available in Stardrop 6.5? The answer is no. In fact, we're already on Stardrop 6.6, and we are releasing very shortly Stardrop 7, and it's Stardrop 7 that will provide the link to the Cerella platform. They are two distinct platforms. Cerella and Stardrop can be used independently. They don't rely on one another, but of course, as we've demonstrated, they form a seamless ecosystem. So if you have both, you can get the best possible value. Another really good question here. How do Alchemite models compare with other machine learning methods in terms of predictions having a lower dynamic range than the experimental values? I'm not quite sure how to interpret that question. So the predictions have a lower dynamic range than the experimental values. So meaning the distribution for the prediction is lower than the range of the experimental data. Well, typically that's what we're looking for. I mean, we would like the prediction to have a smaller error bar than the experimental value, because that will actually give us the ability to resolve within that experimental scale. I wonder if might be talking about extrapolation to values that lie outside of the already observed range of experimental data. And I think you've got some really good information on that, Gareth. So let me pass over to you.
Yeah, so thank you, Matt. So I think that, yes, there's the extrapolation is a very important problem, and that's always going to be crucial when we are discovering something new, entering new chemical space. So in that case, the Alchemite can rely either on its knowledge of, as it starts to extrapolate, the uncertainty typically will start to grow because we're not quite sure where the curve goes. And then coupled with Cerella, it's able to understand how far it should extrapolate, to extrapolate enough that the predicted value will get better, but not so far that the increase in uncertainty will become too much. Now, we have a secret trick to improve the quality of our extrapolations, which is the ability to correlate between different experimental endpoints. And that it may well be the case that one experimental endpoint has already been measured in this extrapolatory region, and then Alchemite's able to use that as a guide to help guide the extrapolation of this other experimental endpoint out to that region. Now, the other comment to add on a different interpretation of that question is about whether Alchemite can reduce the uncertainty in its predictions below that of the underlying experimental data. So we can sort of make one clear mathematical statement about this, that there's one regime where if the underlying expected curve is just completely flat or constant, and then we have some scattered data, then we know from our university level mathematics that the standard error in the mean will go as 1 over root n of the number of data points that's entered that. And Alchemite can precisely pick up on that and precisely replicates that result.
Thank you very much, Gareth. Gosh, there's lots of questions coming in. I think we'll get through a couple of more. Another great question. Do you find it helpful to be able to ask how likely is it that compound X will pass a threshold rather than how far above the threshold is the prediction? And absolutely right. That is a very important point. You probably know, some of you in the audience, that our probabilistic scoring method is based on exactly that principle, which is to take into account not only the value relative to your criteria, but also that uncertainty information, in this case generated with Alchemite. That allows us to say, well, how likely is that compound to achieve our objectives, not just is it much bigger? And that is a really important question. Something that is much bigger with a huge uncertainty really doesn't tell us much, whereas something even close to the criteria with high confidence of being on the correct side is a very valuable point. And it's really key to our philosophy of how to approach this multi-parameter optimization challenge. Here's a great question. Does a low confidence value reflect an underlying unknown unknown, a factor, in this case, like a transporter that alters the outcome for a specific compound in an unpredictable manner?
So I think that that's a brilliant example of where there can be information hidden in the noise itself. So one example in this case would be by delving into the underlying probability distribution, of which we saw some beautiful examples, that sometimes, in fact, the final example we saw had a double peaked probability distribution. And that's really that there's a hint that there's some hidden variable that would distinguish between one peak or the other peak within that distribution. But there are other examples of where now the very sort of bleeding edge of Alchemite, we can take absorb information about the probability distribution itself. So we can use the standard deviation in one quantity may be correlated to the expected value in another. And we're working very hard in order to really be able to pull out and exploit that information to improve the predictions still further.
Fantastic. And I think we've got time for just one more question. I can see one here. Yes, so notice that we emphasized accurate versus precise predictions. Are the predictions truly more accurate or just more precise because of the addition of molecular properties that are known with certainty? So what we demonstrated very clearly is that where the model has the greatest confidence, i.e. the smallest error bars, that represents the most accurate predictions. And this is a really key factor because you don't want to be making decisions based on data which does not have sufficient confidence. It also means that even when you have a model that overall might perform quite poorly, there is very often a subset of predictions which have sufficient confidence for you to use. So you don't have to throw away the results from the model entirely and say, no, I don't trust any of them. You can still pick out that sort of gold dust in there where there are really valuable results. But the question about, is it more precise because of the molecular properties that are known with certainty? Well, again, this relates to the relationship between experimental endpoints. I think I'm right, Gareth, and correct me if I'm wrong, but because it understands what is the most important data with which to make that imputation, so where there's really important measured value, if that is available, that will give you much higher confidence in that resulting imputed value as well. But equally, where it's not available, you've seen from the suggest example that Greg showed you, it could say, well, go and measure that point, and then I can help you to make a better decision. Well, again, I am afraid I can still a couple more questions that are coming through, but I'm really well aware that we're now well over time, and really do appreciate those of you who stayed on the line for your patience. We'll get back to you with any other questions that we haven't answered live by email, so please don't worry, we will respond. But I want to just get on to the final point. Just a reminder, I gave you a little teaser about another case study of the application of Alchemite, this to predicting pharmacokinetics. We saw some questions about that already. So if you'd like to know more details about this, please join us and Nigel Green from AstraZeneca and our colleague Tom Whitehead from Intellegens, and we'll be talking much more about that project, the data and the results. That's on the 11th of November. And if you go to our website, you'll find a link where you can register for that event. And last of all, a big thank you to everyone for joining us today, and for particularly those of you who stayed sort of beyond the allotted time. Just a reminder that this webinar will be posted to our online community probably by tomorrow, and we'll be happy to share a link with you. And of course, you're very welcome to share that with any of your colleagues who might be interested to learn more. So once again, thank you very much, and have a good evening, a good midday, or a good morning for some of you who I see have joined us from Asia. So thank you very much.